In this video, the introduction to the ChargeMol program is going to be displayed. Let's start by talking about the structure and methods of the ChargeMol program. Atoms in materials, AIM methods, use the information generated by quantum chemistry methods to compute properties such as net atomic charges, atomic spin moments, bond orders, and others. These atomistic descriptors serve us to gain a conceptual understanding of materials, and they can also be used to construct force fields to use in classical atomistic simulations. AIM methods link quantum chemistry and atomistic simulations, since they facilitate parametrization of force fields using automated methods from quantum chemistry. The ChargeMol program is a computational implementation of the standard atoms in materials framework, which includes methods to compute density-based AIM properties, orbital-based AIM properties, and a library of reference atoms. This video is going to focus on the blue highlighted sections. The isolated reference atoms library is necessary as it is used to do the charge partitioning. The charge partitioning results are a starting point for the spin partitioning, if needed, and bond order calculation. A separate video is going to be posted on the AIM polarizabilities, dispersion coefficients, and orbital-based AIM properties. The ChargeMol program partitions the material's electron and spin densities to get net atomic charges, atomic spin moments, and bond orders. It uses the latest methods to achieve high accuracy, applicability to a wide range of materials, sound theoretical basis set independence, and computational cost, scaling linearly with increasing number of atoms in the unit cell. This flow diagram summarizes the steps the ChargeMol program does to implement the DDEC6 method. The major parts are as follows. First, the input files are read. Then, charge partitioning is performed, followed by the spin partitioning, only for magnetic materials, and then the bond orders analysis is performed. Lastly, other files are created related to the AIM radial moments. To download the program, visit ddec.sourceforge.net, linked in the description. Once there, click the green button to download the latest version of the ChargeMol code. Once completed, click to Show in Folder. Drag it or copy to a separate folder where you keep your programs. If you don't have one, we recommend creating one in your local disk C. In this case, the folder is called computer_programs_information. We then paste the zip file with the code and extract it. Upon accessing the extracted file, you're going to find several folders, a PDF with detailed instructions, and a README text file. The first thing we need to do is to copy the atomic_densities folder to a place that will be easy for the program to access. Important to note here is that the directories must not contain spaces. That is why we use the underscores. In this folder, the reference ion density for every oxidation state of atoms up to meitnerium with atomic number 109 can be found. Then, the ChargeMol Fortran date folder contains the source codes for Windows and Linux, along with the compiled binaries ready to use in Windows or Linux. The third folder has example scripts for job submissions when using Linux. The fourth folder has example inputs and outputs files for different chemical systems that were run in DDEC3, an older version, and DDEC6 for Linux and Windows. The remaining folders contain various utilities and tools. Now, go back to the ChargeMol Fortran date folder and access compiled binaries, Windows. In there, you will find the different executable files for the program. Choose a 32 or 64 bits depending on your computer system type. Then, select parallel or serial executable file. We recommend using the parallel file to allow the program to run on as many processors your computer has. Then, you can choose to use command line code or the graphical unit interface, GUI. For purposes of illustration, the GUI code is going to be chosen here. Double-click the executable, and a message similar to this may appear. Just click More Info, followed by Run Anyway. A folder is going to be open, indicating the program is ready to run. Now, let's talk about inputs. Generally, you need two types of inputs, the one generated by other programs and the one generated by you. There are two possibilities when generating input files by other programs. The input file containing information about the orbitals is a file with a WFX extension. Files storing the electron and spin density on a real space grid include the BAST files ACAR2, CHGCAR, and PODCAR, cube files, and XSF files. As for the file generated by the user, you need the job control.txt file. in which you specify the analysis you want to perform on the system, as well as other important parameters and information about the system. A BASP example is now demonstrated. Now, for the input BASP files, the BASP files must be generated from a BASP run at fixed geometry. That is, use BASP keyword NSW = 0. Any geometry optimization, if desired, must be done in separate and previous BASP calculation. The recommended real space grade setting is prick = accurate, with an approximately 400 electrovolts cutoff. BASP keyword NCut = 400. Higher cutoffs may be used, but increase the computational cost without significantly changing the assigned atom in material properties. If you don't have BASP input files, you can get some under examples_2_run. I'm going to use the lithium manganese oxide as example. Copy the name of the folder and create a new folder in a different directory that is not where you have your programs. In my case, I created a folder under my documents called example_runs. Go back to the examples_to_run folder and notice there are different input files. ACAR0 contains the frozen core electron density. ACAR2 contains the valence electron density. CHCAR contains the smooth valence electron density for all materials and spin density only for magnetic materials. And PODCAR contains information about the number of frozen core electrons. Select and copy the ACAR2, CHGCAR, and PODCAR files. ACAR0 is no longer used, as ChargeMol now uses its internally stored reference core densities, which are more accurate and reliable. Go back to the examples_to_run folder to copy the job control text file and paste it into your example runs folder. Open it to edit. The periodicity along the first, second, and third direction needs to be set to true. Then, you need to change the directory path for the atomic densities. Let's check the location of the file. In my case, I have to go back to find them under my computer_programs_information in my C disk. We then write the correct directory in where the atomic densities library is stored. In my case, C:\computer_programs_information \atomic_densities\. For BASP files, it is not necessary to write the input file name, as ChargeMol looks for the BASP input files. The charge type, DDEC6, is the recommended to use as it is the most accurate. Lastly, we need to include the net charge keyword. In this case, the system has a net charge of 0.0. Save the file and close it. Now that the two types of input files are ready, we can run the ChargeMol program. First, identify the location of the compiled binaries for Windows and open the previously determined one. When the new window opens, go to the directory where you are keeping your examples to run and select the job control text file. Note that the other input files do not appear in the folder. However, they're there and they're going to be used by the program, yet they don't have the job options for the ChargeMol program to run. Hit open and let the program run. Go back to the folder where you have the input files, and depending on the size of the system, the program is going to start generating output files in the same order the program operates. Additionally, you can run two jobs at the same time by opening the executable file again and submitting a different job control text file. Note that the job control text files need to be located in different folders. Open the file with a .output extension in a text editor. Scroll to the bottom of the file. When a job is completed, a message similar to this is going to appear. Else, the job has not finished. Let's now have a look at the net atomic charges file. In the first column, the atomic symbol appears, followed by the X, Y, and Z coordinates in angstroms. In the last column, we can see the result next. Upon scrolling down, we find a more detailed version, including a column for the atom number, plus the same information that we had above. In subsequent columns, additional output information can be found. Now, open the atomic spin moments output. This is only generated for magnetic materials. Following the same pattern as the next output file, we see the atomic symbol, X, Y, and Z coordinates, and the ASMs in the fourth column. Upon scrolling down, the parameters are found, followed by the same information as above, but with the atom's number. Open the bond orders output and we find the same format, with the fourth column now being the sum of bond orders, SBO. Now, when scrolling down, we're going to find the specific bond orders contributing to the SBO of each atom in the unit cell. To better explain the output, here we show the reference unit cell in red with the unit vectors A0, B0, and C0, and the atom lithium number 1 inside it. This line tells us that lithium is bonded to the translated image of atom manganese number 10 in the unit cell with a unit vector of B-1 from the reference unit cell, and that a bond order of 0.002 was found. That is done for every atom that is connected to lithium number 1. Then, the SBO for lithium number 1 is the addition of all the bond orders. The process is repeated for as many atoms the unit cell has, in this case up to atom oxygen 56. A different way to analyze the output is to look at it in a graphic format in YAML, which you can also get from sourceforge.net. Open the folder with the outputs and drag the NACS output to the YAML window. Upon opening, you're going to see the material in its unit cell, which you can rotate. Now, the YAML menu is in the lower right corner where the YAML text is. Click it and then click Open Console. You can also resize by scrolling up and down with your mouse. Let's now go to Display, then Label, and click Number to get the number of atoms to show. For better visualization, the color can be changed in the console using the command color labeled followed by the color. We see now that the labels have changed to yellow and are easier to read. Another important command is to show the results from the output files. For that, we use the command label $P. Now, the numbers reflect the NAC for each atom, and we can check it by clicking on an atom. We use the information on the console to look for that atom in the output file. We see that the NAC indeed coincide. Let's try the same now with the bond orders output. Now, I chose for the symbol to appear as a label, but once again, it is not distinguishable, so we need to change the color. Then, we display the SBO for the atoms. This number can be found here in the output file. You can also find it in the first part of the file, although it is harder as you cannot see the atom number. We now focus on inputs for WFX type files. As before, create a folder with the name of the example you want to run. Now, I'm going to copy and paste the job control from the last example to this one along with the WFX file. We open the input file to make the necessary changes. In this case, we delete the periodicity as it is not needed for WFX files. We also delete the net charge as it is contained in the input file itself. It is necessary to add the keyword input file name. We then proceed to copy and paste the name of the WFX file and add the extension. We save the file and close it. Essentially, the WFX files store all information the ChargeMol program needs to regenerate the molecular orbitals the program uses to make an electron density grid, and it allows ChargeMol to analyze the orbitals. The WFX file can be opened in a text editor, and it contains the Gaussian basis set specifications, nuclear positions, systems, system or unit cell net charge, basis set coefficients for natural orbitals, and natural orbital occupancy. Go to the compiled binaries folder and open the previously chosen executable file. Upon opening, check that you are in the correct directory for the system you want to analyze and select Job Control. Click Open and let the program run. This process can take longer than for BAS files since it needs to generate the density grids. Hit refresh occasionally until the output folders appear. Also, you can check that output file to make sure the job is finished. Outputs are now directly analyzed with YAML. First, the NAC output is analyzed. Notice that now the unit cell is not displayed. Another way to change the label color without the console is by going to YAML, Menu, Color, Labels, and choose the color you want. Then turn on the label display. Another useful command for the next file is the color partial charge, in which the atoms are colored based on the charge. Now we want to look at the results and use the labeled %p command. We see that the atoms information can also be found in the text file. Let's repeat the same now with the bond orders. Since this is a non-periodic system and the bonds are within the system, all atoms are in the reference unit cell. That is, all atoms are in the 000 unit cell. We look for C84 and find the SVO displayed in YAML. Now, we repeat the same process for the ASMs file. A shortcut in YAML is to press the up arrow key and the commands are going to be copied in the order they were used. Now the data displayed are the ASMs for each atom. A very common way to get an error message is demonstrated. I will copy the input files for the BASPO example in a different file. When opening the job control, I'm going to leave the directory for the atomic densities as it is, and run the file. When opening the .output file and going to the end, we find a message similar to this. When this happens, output files are never going to be generated, as the program couldn't find the atomic densities file and quit. To fix this error, you have to specify the correct atomic densities directory path in the job control text file, as explained in the previous examples. For more information about the theory the program uses to calculate NACs, ASMs, and BOs, you can look at the past YouTube videos published. Stay tuned for more videos and tutorials.